In part 3 of load switch design, we'll replace the ideal pass switch with a MOSFET, getting rid of the last ideal switch. We'll take a look into how to select an appropriate part, focusing on reliability and thermal design. In this case, the ambient temp will be high, 90 degrees C. This is what we have so far. The pass element is still an ideal switch, and replacing it will require a logic level part similar to the enable switch. Previously, we were driving the enable switch with 3.3 volts, but now we have a 5-volt rail for the pass switch, so there's a little bit more overdrive available. To keep the design flexible for what will be covered in part 4 and ensure we have no problems keeping the device off, we're going to try to choose a part that's closer to the 1.0 to 2.0 volt threshold range. If we had a higher voltage on the input, say 8 volts or above, a standard part could also be appropriate. Let's take a look at the key datasheet values for a pass switch. The upper left shows the FET in the off state, where the source to gate voltage is close to 0 volts. The first key datasheet characteristic for this state is the drain source breakdown voltage, which is 30 volts for this part. From our requirements, we're only going to have 5 volts from source to drain, so we're definitely good there. The other key characteristic for the off state is the 0 gate voltage drain current, which is the leakage current. 1 microamp at room temp is pretty typical, and we can expect the leakage to approximately double for every 10-degree rise in temperature. For the on state, with 4.5 volts from source to gate, the RDS on for this part is around 60 to 70 milliohms. That's appropriate for the 1 amp current level in the requirement. Last, the gate threshold voltage is provided here too, and it nominally ranges from 1 to 2.1 volts. It's good for the on state since we'll have a good amount of overdrive above the threshold, and not bad for the off state as well. So how do you actually choose a part? You can go to a distributor's website, with the two big ones being Digi-Key and Mouser. Find the discrete semiconductor page and continue until you get to single MOSFET parts. Here you can use filters to down select. In part 1, we discussed the reason for choosing a P-channel MOSFET, so we'll stick with that here. Since the requirement for current is relatively low, the common SOT23 package is the one we'll go with. A future video will look further into transistor package options. For RDS on, keeping nominal resistance below 50 milliohms should minimize loss and be achievable with this package. The max gate to source voltage is chosen to be between 2 and 3 volts to ensure that we have some margin for turning the FET off. With a slightly higher VGS, it should be easy to stick with parts that have a 20 volt rating for VGS max. With these filters, the number of choices shrinks to around 20, and choosing in stock and your preferred manufacturers should get it down to below 10 options. When you're making part decisions for real designs, it can be helpful to make a trade table and list the items that you care about. It can help make decisions and also documents the rationale for the choice you make. We're doing a pretty simple example, so it's debatable whether you'd make a trade table for a part like this, but if it's a load switch that will appear hundreds of times in the design, or if the design will be produced in large volumes, it might still make sense to make a trade table like this. There were 3 parts that look good from the Digi-Key filter exercise, and they're listed in the trade table here. The next period part is a good choice if you're looking for an automotive or higher reliability part. It does come in both standard and automotive versions, and that's usually a good sign when a part is available in both. However, the VGS range on it is wide, from 1 to 3 volts. The diode zinc part has the tightest VGS range, which is good when you're relying on the input voltage for turn on. The Vishay part wins out with RDS on, but not by much, and if this was really the driver for the design, you might consider other options. A larger package, or even an NMOS part with some more effort put into the enable switch design. It is the least expensive option, so it's definitely a good choice as well. Any of these would work, but for now we'll go with the diode zinc part. So how do you actually make circuit designs reliable? One of the main ways that reliability is ensured in electronic design is through derating. There are a few different standards available for derating, with the NASA standard shown here. If you search for derating standards online, you should see some PDF results from government websites come up. The table on the left shows the derated values of the diode zinc transistor. It's pretty straightforward. Just multiply the rating of the part by the derating factor given in the standard. 2 items shown in the table are derated, but they're not from the standard. These are the RDS on resistance and the leakage current. The RDS on value increases with temperature, so it has a positive temperature coefficient. And there's always a plot in the datasheet that shows normalized resistance versus temperature. This factor was around 1.4 at 110 C for this part, so 100 milliohms will be the worst case RDS on for the FET at temp. For leakage current, it's rare to see anything other than nominal in the datasheet, So the rule of thumb is that it will double for every 10 C rise above room temp. At the ambient temp of 90 C, the leakage will increase to about 100 microamps. One other item to highlight, probably the most important part of derating and the biggest impact on long-term reliability, is junction temperature. This is the temperature of the hottest part of the silicon die and drives power dissipation limits. Understanding thermal performance is a key part of electronic design. Luckily, thermal design can be modeled with circuits, which are then solved with regular circuit techniques. In the thermal equivalent circuit model, thermal resistance with units of degrees C per watt becomes resistance. Temperatures like board temp or junction temp become voltages. Boundary condition temperatures like ambient temp become voltage sources, and power dissipated by components is modeled with current sources. We won't get into it here, but you can also model transient thermal performance by adding capacitors. So here's the SOT23 package shown with an X-ray-like view. Inside, the silicon die may be mounted on the same metal used for the drain foot. Bond wires from the die connect to the gate and source feet. There's thermal resistance associated with each interface, say the connection between the bond wire and one of the feet or the foot itself. The die generates heat by dissipating power, which then travels across the paths of least thermal resistance and heats up surrounding areas. The circuit diagram shows an approximation of the heat paths inside the package. Theta J case shown here isn't the Theta JC sometimes quoted in datasheets. Theta JC in datasheets is typically only useful as a comparison point or when a heatsink is used to provide a primary thermal path. Outside of the package, the part sits on the board where heat continues to travel through thermal paths of least resistance. Again, the circuit model shows how all of these thermal resistances might be modeled. The voltage at various nodes can be read as temperature, and the boundary condition is the ambient temperature voltage source of 25 C. For a package like the SOT23, the most useful thermal parameter is going to be theta JA, which is the series and parallel combination of all of these thermal resistances. Combining resistors in series and parallel gets us to the somewhat simpler circuit shown in the middle. To simplify further, you can do one of two things. One is to assume that theta case to board is much higher than the other resistances shown and remove it from the circuit. This is likely to be true since there's no good thermal path directly between the case and the board. The path of least resistance is through the feet of the package. Making this simplification allows you to continue with combining series and parallel resistors until only a single resistor is left. The other approach is to use two star to delta transformations. This is definitely more involved, but would get you an exact solution if the thermal resistance values were available. Regardless of which simplification method is used, the idea here is that the complex resistive network can be simplified into a single thermal resistance, which is the theta JA provided in the datasheet. If theta JA is 166 degrees per watt and the ambient temperature is 25 C, the actual maximum power that the part can handle is about 750 milliwatts. This power level will cause the junction temp to hit 150 C, which is the limit of the part. Hopefully it's clear that Ohm's law can be used to perform this calculation. Using this understanding of thermal modeling, let's dive deeper into power derating of components. Power dissipation of a part is very dependent on how it's tested, and this is reflected by the way datasheets report it. Each datasheet will have slightly different information. The standard power derating graph is shown here. The physical meaning of this graph is that applying this factor based on the ambient temperature will keep your part around the safe operating temperature. So at an ambient temperature of 70 C, only 64% of the rated power can be utilized. The formula for the line is shown here. So let's take a look at the numbers that the datasheet reports. Power dissipation values for ambient temperatures of 25 and 70 C are given. If you take the value given for 25 C, 1.1 watts, and plug it into the formula shown with 70 C as the ambient temp, the result will match the datasheet for the 70 C condition, 0.7 watts. The 1.1 watts itself comes from the junction temperature limit of 150 C. The condition the manufacturer chose for this rating is to power the switch on for less than 10 seconds, meaning they used the smaller thermal resistance highlighted. If we plug 118 C per watt thermal resistance into the junction temperature formula, the result closely matches the temperature limit. If we assume steady state operation, the true max power dissipation becomes 750 milliwatts, the value mentioned earlier. To make the design reliable, junction temperature is derated below the manufacturer limit. For high reliability design, like what is suggested in the NASA derating standard mentioned earlier, the max junction temp is minus 40 C below manufacturer rating or 125 C, whichever is lower. So here it's 110 C. Next, we have a requirement for 90 C ambient temperature, which is much higher than the 25 C room temp. So what's the actual power dissipation limit for this part? So derating the junction temp and including the environment you're operating in is the key to reliable design. First, define the max power of the part based on the 110C limit. The limit temp minus room temp divided by theta JA for the package gives you maximum power dissipation. You can do a sanity check to see that this number gets you to 110C. Then you can use the chart from the previous slide to derate power dissipation based on the required ambient temp. At 90C, the power dissipation of a part listed as 1.8 watts on the datasheet is 120 milliwatts. That's a huge reduction, but this is how you get reliability. Two notes on this. One is that this is the rating for very high reliability. We're talking about spacecraft, aerospace, medical devices. Your application might be different and may come with its own derating standard. If you're optimizing for cost, this is not the correct approach. The other note is that 90C is very high ambient temperature. Again, the approach has to get tailored to the actual application. We're trying to do a high rel design now, so this is what we're going to stick with. A 1.8 watt part derated down to 120 milliwatts. Next up, we'll download the SPICE model from the manufacturer and add it to the LT SPICE sim. This is the easy method. Download the file, open it in a text editor, and copy and paste it into LT SPICE as a SPICE command. You can use the keyboard shortcut or go to Edit SPICE Directive. Then you can place the model text directly into the schematic. Next, add a PMOS part, control right-click on it, and change MP to XP in the prefix line, and then change the value to the name of the model. So the sim now runs with the manufacturer model, and the output is 4.97 volts, so there's 30 millivolts of loss due to the pass switch. The power dissipated in the part can be calculated with I²R, and you get 100 milliwatts, which is below the 120 milliwatts derated limit. The basic load switch design is complete, and you should be able to tailor the design based on your own requirements.